Hello and welcome back. In this video I'm going to be talking about another method of counting. In this case we'll be looking at combinations. So a combination of items occurs when there are three things that we're going to look for. First of all, the items are selected from the same group. Secondly, no item is used more than once. And three, the order of the items makes no difference. Now in another video I talked about permutations. And so in a permutation, the order of the items was significant. So that's the big difference between combinations and permutations. The notation that we use for combinations is a capital C with a subscript that precedes and one that follows, N and R. So N is the number of items in we'll call it the pool. So this is how many things you have to choose from, and this is the number of items that are actually going to be selected. So we use a quotient that involves factorials. In the numerator we have n factorial, and then in the bottom we have n minus r factorial and r factorial. Now these two numbers, n minus r and r, of course those are going to add up to n. Basically we're breaking up our pool into two groups. A group of items that are selected and a group of items that are not selected. So let's look at some examples here. A 4-person committee is to be elected from an organization's membership of 11 people. How many different committees are possible? So this is a combinations problem. You can think about it, either you're selected or you're not, but when you are selected, there aren't the order in which you're selected isn't going to matter. Everybody who's selected is going to be on the committee. There's no rank among those who are selected, so we can write out the combinations here. I have 11 from which to choose, but I'm only going to be picking 4. So this is 11, choose 4. So I'll take 11 factorial, and 11 minus 4 is 7 factorial, and then I have 4 factorial. Now again, 7 plus 4 is 11. These are the people who are selected, these are the people who are not selected. And now I can simplify this. 11 times 10 times 9 times 8 times, and I'm just going to write 7 factorial, because all the factors of 7 factorial are going to cancel with the 7 factorial in the denominator. So I'm going to just be able to mark those out. And if I'm doing this by hand, I might be able to do some other simplification. For instance, I notice there's an 8 in the numerator and a 4 times 2 in the denominator, which is 8. So all that's going to cancel. And if I want to, I could reduce this by a factor of 3. 9 divided by 3 is 3, and that just makes it a little easier for me to do this in my head. I have 11 times 10 times 3, and 11 times 10, that'd be 330, and then this is over 1. So there are 330 ways that I can do that. Now, I want to point out, here I said a 4-person committee is to be elected. Now there's no distinction among, like within this committee, so that's why I'm saying order doesn't matter. If you were appointing people to offices like president, vice president, treasurer, and secretary, then the role of each person selected is different, and selecting person A as president is different than selecting person A as vice president. So the position makes a difference, so order matters. That would be a permutation. But here, you're either on the committee and everybody there is equal, or you're not on the committee. So that's a combination. Next, let's see. There are 14 standbys who hope to get seats on a flight, but only 6 seats are available on the plane. How many different ways can 6 people be selected? So we have 14, but we're only going to choose 6. So we have 14 factorial, and 14 minus 6 is 8 factorial, and then 6 factorial. So again, 8 plus 6 is 14. These are the people who are selected, these are the people who are not. But the order in which you're called, you may feel like if you were on a standby list, you'd rather be called first, but really, everybody who's selected gets a seat on the plane, And so the order that they're called doesn't make any difference as far as who actually gets a seat on the plane. So let's simplify this. I have 14 times 13 times 12 times 11 times 10 times 9 times 8 factorial. I have 8 factorial in the denominator, and then 6 times 5 times 4 times 3 times 2 times 1. All right, so these factors are all going to cancel. And let's see, I might be able to reduce some other things. 5 times 2 is 10, that cancels. And 3 times 4 is 12. I can get rid of that. And let's see, 6 is 3 times 2. So let's see, if I reduce by 3, I'll be left with a 2 here and a 3 here. And then I could reduce this by with a factor of 2, and that would just leave a 7. So I have 7 times 13 times 11 times 3. And that's all just now going to be over 1. So 7 times 13 times 11 times 3 is 3,003. Okay, so let's look at another example. To win a lotto game, 5 numbers must be selected from 50. The order in which the selection is made does not matter, so we know immediately that this is a combination. How many different selections are possible? Well, I have 50, but I'm only going to choose 5. And so I'll take 50 factorial, and then 45 factorial, and 5 factorial. So this is going to be 50 times 49 times 48 times 47 times 40, times 46 times 45 factorial. And then here I'll have 45 factorial, and 5 times 4 times 3 times 2 times 1. These are all going to cancel. In this case, I'm not going to worry about trying to simplify ahead of time. I'm just going to, I know that 5 factorial is 120 from previous work. I'm just going to figure out what, let's see, 50 times 49 times 48 times 47 times 46 divided by 120. And so this is 2118760. So 2,118,760. Okay, and then let's look at this last example. How many ways can a committee of 4 men and 4 women be formed from a group of 7 men and 7 women? So we're going to have a committee with 2 parts, and we need to choose, I'm sorry, this would be choose, I'm sorry, I'm writing this wrong. For the, this is be the men, and this will be the women. I have 7 men, but I want to just choose 4. I have 8 women, and I'm going to choose 4. I'm combining here my combinations with the fundamental counting principle. So I'm just breaking this up into all the possibilities for the different selections of men, and then all the possibilities for the selection of women, and then I'll multiply those together, and that'll be the total number of ways to form this committee that's equal 4 men and 4 women. So 7 choose 4 is 7 factorial, 3 factorial, and 4 factorial. And 8 choose 4 is 8 factorial, and then 4 factorial, 4 factorial. So let's see, this would be 7 times 6 times 5 times 4 factorial over 4 factorial over 3 times 2 times 1. So those will cancel, and 3 times 2 will cancel with 6. So that's 35. And then 8 factorial, 8 times 7 times 6 times 5 times 4 factorial, and 4 factorial, and 4 times 3 times 2 times 1. These will cancel. 4 times 2 would cancel with 8, and 3 would cancel with a factor of 3 and 6. And so I'll have 7 times 5 is 35 times 2 is 70. So in the end, I need to take 35 times 70, and that's 2450. So every different of the 35 possibilities in the men, each one of those could then be paired with any of the 70 groups of women that are selected. So each one of these could be paired with any one of those. So that's why I need to take 35 times 70. And that will give me the 2450. So I hope that helps with an understanding of combinations. Again, it's easy to, or sometimes it's hard to decide whether you should use combinations or permutations. Just remember, if the order has significance, you need to use permutations. But if the order of the items makes no difference, it's a combination. All right, see you next time.